Okay, thank you, Sam. Thank you for kind introduction. Well, first of all, thanks for inviting me to give this talk to your community. So, assuming that the community is mostly dealing with quantum fluids, so superconductors stuff, so I'm gonna give a bit of introduction to magnonics and to all the stuff why we are doing that in actually in solid state things. So so let me, okay, well, it's not, okay, should go, okay. So basically, when it's dealing with everything quantum, nowadays people think about like quantum computing perspectives of that. And indeed, in comparison to classical computing, quantum computing has some advantages, though it has some disadvantages. It's not all-purpose computing, of course, but you can solve several problems like breaking ciphers or actually computing the commute problems and also sorts of sorting or seeking the entry in the database. So all these could benefit from quantum computing. And of course, nowadays, everything dominated by the superconducting circuits and also some ion-based quantum computers, qubits. However, it's interesting to look for something else, for some other technologies, some other physical systems, which could allow some interesting features which are not present in or even not achievable in the superconducting circuits. So basically, for specific tasks, as I said, the performance of the computing goes from classical to quantum. And with that, which I'm going to talk about today, we are somewhere in between the specialized data processing with wave packets and between quantum computing. So we are in the macroscopic quantum state computing. So, and I'm going to describe this in a bit. So for the purpose of operating with quantum states, we need the carriers of these coherent quantum states. And for that, we need coherent data carriers. And one of those carriers could be, and it's proven in cold atoms, that it could be Bose-Einstein Condensate. So how we can get condensate? Well, we can cool down cold atoms, but actually we can also utilize some quasiparticles. And one of them is the quasiparticle associated with the precession of the magnetic moment. So, and to explain where this particle originates from, let me start with a very brief introduction to the ferromagnets and spin waves. So basically, in ferromagnetic material, where the atoms are having unpaired electrons, and they have the magnetic moment, these magnetic moments are aligned along each other due to exchange interaction. But if you take just one that moment, you tilt it from equilibrium orientation, then if you do so, it starts to process along the equilibrium direction of magnetization. But in addition to that, it also interacts with others via exchange and dipolar interactions. And that produces a wave, which is called spin wave. For that wave, we can obviously define the wave vector. And properties of these waves are described by a well-known Landau-Lifshitz-Gilbert equation. Although this equation is well known, the And the solutions in partial cases are quite simple. In general case, it's quite a complex equation, which includes different sorts of interaction, nonlinear interactions. It is an intrinsically nonlinear interaction. There are different effective fields which influence the precession, influence the energy of the spin waves. So it's external field, it's a dipolar interaction field, exchange interaction, anisotropies, magnetoelastic interaction. So there are many things which could be used for tuning the energy of spin waves and changing the dispersion. So, but is this only a wave? Actually, in terms of quantum language, every wave could be expressed as a quasiparticle, and magnons are the quanta of spin waves. Then, and for them, we can define energy, momentum. Obviously, it's interesting that for the material in which we are working, the effective mass of such quasiparticle is about 6 times larger than the mass of an electron, although it's spectral dependent. So it's and it's still under discussion whether mass makes any good physics in there. But what's more important are the last 2 properties listed here. One is this spin is equal to 1 because one single magnon is associated with this spin of electron flipping from up to down. So, and that's 1/2 plus 1/2, it's 1. So, and the second important feature is that we have strong nonlinear interaction. Basically we have 4 and 3 magnon scattering processes, which effectively could lead to magnon gas thermalization. So if we consider this ensemble of magnons inside of our ferromagnet as a gas of quasiparticles, then we can get all the interesting quantum phenomena in this gas. Of course, the distribution is described by Bose-Einstein formula. So, and in log-log scale, it does look like this. So magnons, in contrast to real atoms, they do decay. So it means that in thermal equilibrium, chemical potential of magnons is 0. So if you quasi-statically change the temperature in the system, it will not give you ability to achieve high chemical potentials, which is necessary for Bose-Einstein condensate. So, so how do we get from this spectrum distribution to this one then? Well, the answer for that is essentially to increase the number of magnons in the system. So, and that we can do by different means, actually. So before I start with describing actually how we do that, let me speak about the medium where we do the experiments, because this is quite important. We have many different kinds of ferromagnetic materials. It ranges from well-known permalloy, cobalt iron boron, Heusler alloys. So these are very popular nowadays. You can make a very thin layers of it, very nice, but the damping of magnets in such materials is very high. So if for the damping, the best material known so far is yttrium iron garnet. It has up to like 700 nanoseconds lifetime at room temperature, and at low temperatures it could be even going beyond 1 microsecond. So this is already phenomenal. There were no other materials with such damping so far discovered. So So that's why we stick to this material. This is ferrite. It is oxide. There is no conduction losses. There is no and it's very chemically stable. So and it could be grown in thin films, or it could be grown into nice crystals, which could be shaped into spheres, which are very popular nowadays in field of quantum magnonics, by the way. So, okay, magnons in yttrium iron garnet and in any ferromagnet, actually, they have quite interesting and anisotropic spectrum. So if you solve the Landau-Lifshitz equation, including all the fields and boundary conditions for the thin film, you will end up in the dispersion, which looks like this. It's a set of modes which are different for the direction propagation along the field and perpendicular to the field. And if you look into the cross-section of this longitudinal direction, and you especially you look around the minimum of the dispersion here, in 2 dimensions, dispersion looks like this. It's like a saucepan, right? And this dispersion has a very intricate feature that the wave vector of the minimum, the dispersion, is not at 0 wave vector, in contrast to the cold atoms or electrons. So this is distinct feature of magnonic spectrum, and that associated with some difficulties how to actually detect this Magnon condensate, which will apparently occur in that minimum. So, well, but first, how we inject more magnons into our system. So in our system, we can do that in many ways. So one of the most conventional ways is to use just ferromagnetic resonance and drive the precession strongly, but that is associated with a lot of unnecessary heating due to the relaxation of magnons in the ferromagnetic in this state before they thermalize. So the more effective way of creation of magnons in the system is to use so-called parallel parametric pumping. So in our system, in a thin film, the precession of magnetization, it's not circular, it's actually elliptic. And because of that, the longitudinal projection of the magnetization along the bias field direction oscillates at twice higher frequency than the precession does. If we apply external field at the twice higher frequency than precession, we can essentially couple to that field to this precession and amplify the precession angle. In quasiparticle language, this is expressed as splitting of one photon of pumping into 2 magnons at the half of the pumping frequency with conservation of momentum. And that produces us from 1 photon 2 magnons already. So this is a quite efficient process for us. And essentially this photon is not exciting any magnons in the system, so this is not producing any additional heating of the system. So when we strongly pump magnons into the system at these 2 points here onto the perpendicular branch of the spectrum in this case, we get strong nonlinear scattering. And this nonlinear scattering causes the groups to scatter over and create incoherent magnon gas. So, and this process conserves number of magnons. So within the damping of the time of the decay of the magnons in the system, we consider our system as a conserved number of particles system. And eventually, if we pump the system strongly enough, in the minimum of the spectrum, we will expect formation of Magnon Bose-Einstein Condensate on top of the overpopulated spectrum. So I started the description of the system and with the saying that it's quite problematic to see these points, to detect them. And the difficulty is associated with a high wave number and very short wavelengths of these magnons. So the wavelengths typically is about a few microns. And the thinner the film, the higher is that wave vector. So how to detect 1 micron wavelengths magnons? Well, magnons produce electromagnetic fields around. So this is essentially magnetic wave. But the problem is to fabricate the micron-sized antennas to do so. And if you fabricate some coplanar waveguide antennas on top of each magnon, it might change the boundary conditions and so on. So the easier way, moreover, the more wave vector selective way is to use non-destructive optical spectroscopy techniques in order to detect it. So the tool of choice for us is the brilliant light scattering spectroscopy. So which is nothing else as inelastic scattering of photons on spin waves. So we have one photon of the laser light. We use typically green laser 532 nanometers, and it scatters on magnon. And because of the conservation of energy and momentum, we can have frequency resolution. Of course, we have to use sophisticated interferometry to get the frequency shifts on top of 550 terahertz of the light. We need to detect frequency shifts of around a few gigahertz. So this is requiring tandem Fabry-Perot interferometry, and thus we don't have very superior frequency resolution there. But we do have enough resolution to actually measure the spectrum in frequency and conclude that it has Bose-Einstein shape, and also we can see some features in there. But in order to detect purely the condensate, well, we need to beat this wave vector uncertainty, and in order to do that, we use wave vector resolution. In order to do so, we utilize the backscattering geometry with the reflector on, beneath the sample. So in that way, if our scattering light only reverses the in plane direction of its wave vector, the other component is reversed by the mirror placed under the sample, and thus the scattered light goes backwards at the same direction as the incoming light, probing light. So the wave vector of the spin wave in such a case is coupled to the wave vector of the laser and the angle of incidence. And changing that angle of incidence in our apparatus, it actually works pretty much like this. So we rotate the beam around the sample placed inside of the magnetic field, like that. And thus we can have wave vector resolution, which is, if you look into the scale, it's pretty much in scale with this picture. So we can cut off this box to map the dispersion. So our overall apparatus to measure it consists of course, the interferometer to detect and discriminate by frequencies our light, and excitation laser, which is not exciting the magnons though, but it's actually used for probing, right? And but excitation of magnons is done by microwaves, so microwave generator forming pulses and high power amplifier. And then the excitation itself happens by microwave resonator. So Well, the experiment is done in wave-vector time frequency space. So in order to analyze it, we need to slice the data into the right ways. So if we take the dispersion around the minimum and we rotate it like that, and essentially, because we don't have very good frequency resolution, let's integrate over the whole frequency range here. So here's the wave number versus time. And if we apply pumping not so large, what we'll see that after we apply the pumping pulse, magnons start to go to the bottom of spin-wave spectrum and essentially start to form Bose-Einstein condensate peak at the bottom. Well, we wanted first to get more magnons then. So more magnons in condensate, we increase the pumping. And what we've seen that at large pump power, it unfortunately doesn't work like that. We don't have any population during the pumping pulse, although we have a lot of magnons in the gaseous phase at high wave vectors, so basically over here. But where are the magnons go? How they, whether they condense or not? Well, if we look at the Bose-Einstein distribution, actually, if you look at the temperature of this gas during the pumping pulse, of course, it's quite tricky to treat the system under pumping as equilibrium. But just if we do that, we find that effective temperature of this gas is 30,000 Kelvin. So, and essentially, this is the gas around the bottom. It's not at the point where we pump it. We pump it essentially a couple of gigahertz higher by frequency. So we are looking at already thermalized gas here, but it's strongly overheated by the pumping thermodynamically. When we turn off the pumping, then Magnon Bose-Einstein condensate essentially forms in the end. And this is associated with a process of evaporative supercooling, which is known in the, if you just have a mug of coffee and you see the vapors coming out, this is how the coffee cools down very effectively, thus the Magnon condensate also. So, but this is just a process how we form Bose-Einstein condensate of magnons, and this is one of the ways. Can we do this differently? Yes, the answer is yes. We essentially recently we discovered that we can actually get Magnon condensate also by doing rapid reduction of the temperature on the scales of much faster than the relaxation rate. So let me quickly describe you how it works. So when we heat up our system, phononic system, basically we just heat up the sample to higher temperature, we get larger number of thermal magnons in the population. So, but still chemical potential is zero. But if you look at the excess number of magnons, it's huge here in comparison to the minimum, to the room temperature. So essentially, if you take down the temperature much faster than the magnons can relax to the lattice, all that excess magnons will stay in the system. And because of the nonlinear scattering, they could form the condensate. So, and essentially at very high frequencies, the dominant processes for this scattering are 4 magnons and also Chernkov's process scattering, which essentially even enhance the flow of magnons toward the condensate. So, and essentially, you can expect that that Magnon condensate will form at some particular threshold of this cooling rate. So, but how to make this fast cooling? Well, with large macroscopic samples, it's very tricky and not really possible. Well, you need to create a huge gradients in temperature. But on the nanoscale, though, it's possible to achieve that without even using some cryogenics. So for this experiment, we used thin Yig film of 17 nanometer thickness. And of course, the size of the structure was 500 nanometers wide and 4 microns long stripe. So this, in such stripe, in order to probe it, we had to shrink down the spot of the probing laser to this 500 nanometers. So that's why the vector resolution, obviously because of the uncertainty in vector due to the small spot size, was not possible. But we still have frequency resolution in there. So, and we still observe it with BLS, obviously. So how this cooling works? Basically, the sample is so small that the heat which is deposited by the titanium, gold, and platinum heater deposited on top of the sample is actually that heat takes just few nanoseconds to dissipate to the substrate. So, and substrate is pretty massive. So, well, let's actually look what happens with this with the system. So, what we essentially have here now it's not populated, but just thermally populated spectrum. And in thin film, in a waveguide, we have some edge modes, we have some thickness modes of the spectrum. So when we heat up our system, then of course it's ferromagnet, magnetization goes down, and we heat up almost to Curie temperature. So you can see that the signals, BLS signal vanishes almost because of the magnetization going down. So, and that's why you can see that the frequencies goes down as well. But then when we heated up our system, it's pretty short pulse, 150 nanoseconds, and then we stop heating and allow our system to cool down, and we see that there is a huge peak of magnons forming at the bottom of the spin wave spectrum here. Well, is it a Magnon BC? Well, we don't have the means to explore it via wave vectors, and we have only frequency distribution. But in order to prove that, we have also the higher energy states. So we have frequency distribution of magnons at every time here. So we can actually essentially utilize that in order to prove it. So of course, we can make slices of the at particular frequencies. So this is the bottom. So here how it goes. This is that essentially that pulse which I showed you. First, we wanted to prove that our system is not prone to any kind of spurious effects. So what we did, we changed the time of the switching off of the heating pulse. So in that way, we prolong the time for cooling, and obviously our effect depends on the cooling rate. So if we increase it to 50 or 100 nanoseconds, the effect is not present. So, and obviously the effect is not dependent on how fast we heat up the system before. So if we just heat it longer and slower, it doesn't really matter. Only cooling rate, what matters. In order to prove that it's a Bose-Einstein condensate, we developed a model. And in this simple model, we just assume discrete spectrum of magnons. We split our spectrum into discrete levels up to 6 terahertz. And we assume only short range for magnon scattering interactions only. The interactions via Cherenkov processes are much more difficult to model, so we excluded them from this simulation. Well, if it works with the simple model, then obviously with enhanced scattering, it will work even better. And the dynamics of the scattering is basically described by this dynamic equation, nonlinear equation of the population numbers. So we have this n equation for each state, and here is our density of state for our quadratic spectrum in 3D case, and amplitudes of 4 magnon scattering term is as follows. So with this set of equations, we just throw it in the numerical system, and we model it. The modeling of the system happens basically in time. We look at the evolution of the system, and we start with already heated up state. So here is the lattice temperature. Here is the chemical potential of the system, which we can compute from our theory. Because we have access to all the frequency distributions, and the population of the lowest state is also very well available for us. So at zero moment of time and during the stable temperature period, we have chemical potential equals to 0. But then we start to turn off the heating, and actually in model we do the instantaneous cooling. So immediately the number of magnons at the bottom starts to increase, and the chemical potential starts to rise. And the distribution, you can see it's depicted here, and it goes higher. So you can see that the relatively small change of the magnon population here causes the huge population change at the bottom spectrum. So because of the energy difference here. So like 1 magnon at terahertz frequencies could produce a ton of magnons at the bottom. And then, well, the magnon density increases, and then at some point it forms a peak. And this peak appears exactly when the thermalization, when the chemical potential touches the frequency of the bottom. This is formation of the Magnon Bose-Einstein condensate. Of course, magnons do decay, and thus the population decreases. The higher the temperature is, of course, the more magnons we will get here, the longer this condensate would live there. And essentially, after a sufficiently long time, we see that the system returns to its equilibrium state at T minimum. So we did comparison with our theory, and we see that essentially it works, although there is some discrepancy between that. But again, we have not taken into account many properties of this system, like Cherenkov's processes. Yeah. So later on, we figured out that we can calculate the chemical potential out of our experiments. We can use the higher order modes in order to get the chemical potential of the system by comparing the population at the bottom and that mode. So, and using that method, we were able to extract the chemical potential, and indeed confirm that the chemical potential touches the frequency of the bottom of the spin wave spectrum at the time of the appearance of the peak at the bottom. So this is indeed the Magnon Bose-Einstein condensate achieved by rapid cooling. So, and we did additional tests in order to exclude the effects of spin pumping from the platinum. So additional generation of magnons from platinum heater, it does not occur. So our signal is symmetric in respect to the applied current direction through the platinum heater. So, and we did also experiments with other metals like gold and titanium. So it also works. All right. Now I would like to just use the condensate, Magnon condensate, and move it around using some gradient. So I want to create a supercurrent in it, and in order to do that, in the classical superconductor, in order to create the difference in the phase, you just apply voltage across the tunnel barrier, and then you end up in the different phases. Well, here what we can do in order to induce the phase, since our magnons are waves, well, we can tune up a bit the frequency of one portion of the condensate, and then expect that over time that will develop into the phase gradient. So, and how to change locally the frequency? Well, we have this nice temperature dependence of the frequency of the bottom, and as we change the magnetization, and magnetization depends on temperature. And thus we can tune the frequency of the bottom by 29 kilohertz per Gauss, or which translates for yttermanganate to 116 kilohertz per Kelvin rate. So we can change the trade-off in time, the gradient in frequency for the gradient in phase. How to heat up the system locally? Well, we have perfect heater, which is actually our probing laser. And that was the very first way to induce the supercurrent in our system, to use the probing laser. So how it works? We take our, for this case, we take our macroscopic thickness YIG. We take parallel pumping, and we look at the condensate evolution at the end of the pumping pulse. So in log scale, it looks linear. Well, it's just exponential decay of magnons. And then on top of this free evolving Magnon BC, we start to increase the laser heating by increasing the probing laser pulse, both power and duration of the illumination. And then we start to see that as we increase the probing laser pulse duration, we increase the heating, and we see that the dynamics goes from the linear in log scale goes to nonlinear, and this dynamics has strongly changing slopes at the beginning, and then at some level it turns into the same relaxation rate back. So, which is associated with here at the bottom, at the lower population, it's a Magnon gas, and at the higher Magnon population, that's a Magnon BC. So, how Magnon BC is affected by the heating? Well, this is from the original idea. This is Magnon supercurrent, and in order to prove that, and in order to figure out what happens, actually how that condensate flows out, we did additional experiment And for that, we separated the heating and probing. That was the next step. And we used for heating another wavelength laser for 5 nanometers. And we scanned over the condensate with the green laser, and we scanned over the heated spot. And indeed, when we went through that spot, we've seen that the condensate is actually going from the heated spot, leaks out to the outside in the form of a pulse. And if you turn this picture a bit into the space map, and now I will show you a movie of the space versus Magnon population. So, and here the red curve is the temperature distribution simulated in our system with COMSOL. We achieve the temperature difference about 40 Kelvin in the hotspot. So first time we pump our condensate, and despite of the heating, we have equal population of the Magnon condensate in all spots. But then, after some time, we form the well in the population, and at the edges of this well, we form peaks. Magnons are pushed away via supercurrents. And then these peaks, these peaks propagate towards the edges of our observation area. And everything happens on top of the decaying condensate. So, and please notice that after initial push from this area of the gradient, we have propagation outside of the gradient area, where the gradient is almost not present. So this is obviously cannot be due to the supercurrents anymore, which are originating just from the phase gradient. So where it comes from? Well, as you can see, this initial gradient produces these peaks, which are indeed the excitations of the condensate, with some characteristics widths. And this excitation propagates actually at the velocities around 400 meters per second. This excitation, we can plot it at different excitation heating powers, basically for different widths of the pulse, and that gives us dependence of the group velocity on the time. On the first glance, it's linear, but wait a moment, it's not really linear dependence. So just to give you that movie into a static picture like that, so that you can see how the propagation happens. So yeah, this is the initial push from the local heating happens in the form of supercurrents, but then essentially outside what we have secondary excitation of the condensate, which is a second sound pulse. And in order to model it, we use Gross-Pitayevsky equation, and here comes handy the dispersion, which I have shown you at the beginning of the talk, where the dispersion looked like a saucepan. So there, the dispersion in perpendicular direction to the magnetic field is steeper than along, and this is essentially the direction perpendicular to the magnetic field. It's the direction in which the supercurrent pulse is propagating, and it's into which the second sound pulse propagates to. And that's luckily the direction where our condensate is elongated along the pumping stripe. So So essentially, because the dispersion coefficient in that direction is much larger, then we can expect that the propagation is stronger, it's faster in that direction. So the stationary solution of Gross-Pitevsky equation is our Bose-Einstein condensate. And the dispersion law for small perturbation of this solution is the second sound. The dispersion looks as follows. And here we have two limits. We have limits of high excitation when we have large wave vector excitation. And for that, we have the dispersion is quadratic. But for small excitations, we have the dispersion which is linear, and that is a second sound. It is proportional to square root of dispersion coefficient, nonlinear for wave repulsive interaction coefficient, and the condensate density. So the group velocity is proportional to the square root of the condensate density. And if we do our estimations for our system, we get it we get estimations pretty close to that what we have in our experiment. We have the estimations of nonlinear shift, which is reasonable for the experiment. And moreover, when we fit our experimental data, we can see that the starting and the final velocities are very different. So indeed, these curves are not linear; they are parabolic. They are sort of square root dependence of the condensate density. And obviously with time, condensate decays. So the number of magnons decreases, thus the speed should decrease. And that is exactly what's happening, and that's exactly what's predicted by the theory. That's why we conclude that this is the Magnonic second sound. So Sam, do I have here some minutes, so like
how much do you
5
need?
Minutes?
Yeah, 5 minutes is certainly fine.
Okay, thanks. So because this is about the Magnon second sound, but I wanted to actually share with you a couple of new developments and new ideas in the field. So Magnon condensate, that's a collective phenomenon. But for quantum computing, in the classical form of it, the computing is done with single photons, single either optical photons or microwave photons. And in this sense, the magnons are also possible to utilize. However, creation of single magnon is kind of tricky. Because, well, to create magnon, you obviously classically need just one photon of microwaves, and then you can convert it using microwave antenna and live with that. So that's fine, but you need a single photon to begin with. And to create a single photon, you would need, well, the most reliable source of single microwave photons nowadays, that's a qubit. And qubits are not quite easy to operate, especially in high magnetic fields, which are required to magnetize our samples. So these are two different worlds which people already combined. And there are experiments of qubit successfully connected via large cavity, transferring the one photon from qubit to the magnonic system. which was a Higgs sphere. But here I want to propose actually the more intriguing and more interesting phenomenon here. So if you look at parametric pumping that I have been described to you to create the Magnon Bose-Einstein Condensate, but look at it from the quantum point of view. This is parametric down conversion process. So in this process, from one photon, microwave photon, we create two magnons. And essentially, there are no limits on how strong the pumping should be in order for this process to work. So this process spontaneously could happen at any pumping level, even if we will throw one single photons on it. So, well, the only difference for this process to that what I have shown you, well, right now it's not different, it's exactly the same picture, but I want to make a difference here because at the perpendicular branch of the Magnon spectrum, if you pump it here, those magnons will not propagate and they will stay at the same spot. So we will not be able to separate them anyhow. So for that, I would just lower the pumping frequency or increase the field, and then start to pump into the longitudinal branch, where the group velocity of magnons obviously is high. So these magnons will propagate in opposite directions. So, and then we'll have two magnons. So, and how we get from two magnons a single magnon? We can use one of them, we can sacrifice them, and use a heralding. This is known concept from photonics, when using parametric down conversion, one of the entangled photons is used to herald the creation of the second one, and thus one can then use the fact that one photon has been generated, one can delay it, and one can use that photon for computing later on. The same process is available here, and here we can separate magnons by using this parametric process, by using generation at longitudinal branch. We can get two magnons at the two branches, two different directions, and we can detect them with two antennas, or we can use them for all magnonic quantum processing circuit later on. So, and we did some tests at room temperature, and this is particularly interesting. So what we did, of course, at room temperature, we use much larger pumping powers to create a huge number of magnons in the system. But essentially what we achieved, we tried to look at the correlations between these groups of magnons here generated into these two outputs. And I will skip for the sake of time the results there, but what you can see that the signals detected are quite resembling each other, and I should stress that these two signals are detected in single shot experiment. So every single realization is different of this process, because every process starts from the generation of from one photon of pumping two magnons, and then these two magnons start to be coherently amplified by the same pumping pulse, which is still applied to the pumping area. And then these signals, as they arise, they are already quantum mechanically basically detected. So their quantum state is very well projected, fixed. So after initial generation of pair of two magnons, which have, in principle, in some conditions, they could be entangled. We generate them, and then by applying continuous pumping pulse, we already fix their phase state, and then we amplify them to the level which we can detect even at room temperature. And then what we do, well, very first try was to do the cross correlation, And indeed, we get correlation more than 90%, sometimes ranging to like 98%, which is quite high for a room temperature experiment. And of course, the maximum correlation and maximum intensity of the generated signal is occurring essentially in the region where we expect the generation of magnons by parametric pumping in this propagating region, like that. So this is the idea. And essentially, with this process, we can try and we can essentially test quantum correlations even at room temperature. And this, I believe that this device, we can create magnons, single magnons in the circuits where we don't need superconducting circuits anymore. So we can create, based on this single magnon source, we can create fully quantum circuits based on magnons, like starting from mimicking the quantum photonic circuit. Well, with this, I would like to conclude my talk. So with conclusions that we can create Magnon Bose-Einstein Condensate even at room temperature. We can generate excitations of this condensate, supercurrents and second sound. And I hope I demonstrated you the concept of the heralded single magnon source, which I believe this is the good way to go with quantum magnonics. I also would like to thank the really large team of people who worked with me on this project in Kaiserslautern, in Weizmann Institute of Science from Israel, from Auckland University, USA, University of Vienna, and in Kiev. And also, I would like to acknowledge help of my grad students, Renju, who is working with me on the single magnon project. So, and with this, I would like to thank you for your attention.
Thank you very much. This is very interesting to follow. I think the first question is by Igor. Please go ahead.
Thank you, Dmytro, for very interesting talk. I have such a question that which concerns the preparation of the BAC. You said that you create magnons at high temperature and then you cool down by evaporation. And you mentioned that you need a strong interaction between magnons and even nonlinear interaction. Why is that? Why do you need strong interaction between magnons to Bose-Einstein condense them? Thank you.
Mm-hmm. Well, it's actually a very good question. So, well, obviously magnons do interact with the phonons with the lattice, right? And this process is leading to both magnon scattering and also leads to thermalization of the gas. Though we need to bring magnons down by frequency. So when we create excess magnon population, especially using parametric pumping technique. So when we inject magnons right here into the spectrum, into these two spectral points, we need somehow to get those magnons thermalized over the spectrum. So in the quantum gas, in the cold atom gas, you don't need interaction of atoms. Indeed, you need, but you need their interaction through the box. Basically, they interact through the box in which those atoms sit. Here we don't have that box. The box, it's lattice, and the interactions of with the lattice at these frequencies happens at the basically relaxation rate. So this is not very effective. It's a very effective interaction at terahertz frequencies. And terahertz frequencies, we also have Chernkov's processes and interactions. So, but we need some interaction. It's not as strong. It's not basically kicking out the magnons from the condensate. It's in terms of the gas, proper would be to call it weakly interacting magnon gas. It would be properly to say that like this. And of course, if we increase the number of magnons, it starts to interact more strongly. But essentially, it's weakly interacting gas. In comparison to the energies of magnons itself, so the interactions are in the order of a few megahertz. So this is much weaker than that. So this is weakly interacting gas. It's not. So basically, I didn't use the right wording that time. But, yeah.
Thanks. I hope that answered the question. Then Andre Goldman has the next one.
Okay. Yes. Can you hear me? Yes.
Yes.
Well, I was interested by this Magnon-Cherenkov effect, and my question probably answered a little bit in your answer to Igor Toroshensko's question, but this is a mechanism which involves then your magnon and what, a phonon in the.
Yes.
So how does this affect your experiment? I mean, it's because okay, you have a quadratic dispersion relation for your magnons, and they can decay because they are not real particles, and this is because they exceed the speed of the sound of the phonons in your.
Yes. Yes. So,
that's a mechanism of decay, which is normally weak, but in your case is of importance.
Yeah, it's quite. It becomes strong at higher frequencies because the quadratic spectrum. So you have increase in the group velocity as
yes,
you go
yeah, sure.
Frequency. And that's that basically that brings the velocity close to the and higher to the velocity of the phonon in the spectrum. And there are tons of phonons in the high up that energies. So there are lots of possibilities to scatter. So this dispersion, which is drawn here, it's the very tiny bit of the dispersion near the gamma point of the dispersion. And those thermal magnons, which we are talking about in this experiment, these magnons here, these are essentially like 6 terahertz magnons, and those are really high.
Decay fast, yeah.
Yeah, they really decay fast, but at the same time, the scattering rate is also huge. Because of the first of all, nonlinear four magnon scattering is proportional to the frequency.
Yes.
To power 4. So it's also these Chernkov's processes are kicking in.
Yeah, it's a very efficient process. Thank you.
Yeah, but the trick is that just using the just simple model just involving the scattering via 4 magnons is enough to actually achieve that effect in theory. However, I should say that we only with very rapid, almost instantaneous cooling rate. So yeah, that is slightly. That's what deviates this theory from the experiment. We have to have very instantaneous cooling. In the experiment, when we estimated that using COMSOL, we ended up in like tenths of nanoseconds cooling rate. But essentially, the Chernkov's processes, which we are not able to model with this theory, they are much more effective at that frequencies, and that would bring a ton of magnons down to the bottom, and obviously give the positive result.
Thank you.
Thanks. Grisha Volovic is the next one.
My question is, how many Bose condensates you have, 1 or 2?
Yeah, good question. Good question. We have the although we look at look at one minimum, right, here, but essentially, in order to propagate into, in order to create how it's created, basically, how, let's put it like this. It is created such that we observe in both minima, we observe the condensate. However,
yes, can be different. Density can be different. Yeah.
However, when we originally pump, like with parametric pumping, we create pretty much symmetric population of the magnon spectrum on both sides. And the recent simulations shows that if we populate the spectrum only on one side, we will actually create the condensate only on the one side. So I tend to think that we do have two condensates.
Then you must have a Josephson, internal Josephson effect, and
Yes.
also the Higgs bosons, the oscillation between them.
Yes.
So,
yes, and the Josephson oscillations has been already shown in Kaiserslautern, actually. So yes, there this effect is present. We have the oscillations between the condensates itself, and so it's possible to cause the condensate to actually go from one wave vector to another.
okay, thanks.
All right, Igor, I think, has a second question.
Yeah, very short question. And you said that the Magnon velocity is 300 meters per second in your system. Is it correct?
The condensate second sound, so the excitation of the condensate is about from 300. It's ranging with the Magnon density, of course. So let me quickly jump to that. So yeah, so it's ranging. So if we go from the beginning of the formation of those pulses, we have 450, but at the end it's 300 meters per second. And this dispersion has nothing to do with the, well, it has to do with the dispersion of the dispersion coefficient of the dispersion of the magnons, but it is not the magnons dispersion, it's the Magnon condensates dispersion. That's what causes that. Magnon condensate stays at the bottom of the spin wave spectrum, so it does not propagate itself without excitation.
Yeah, it just sounds a little bit too high for the, but for instance, what is the speed of sound in this system?
Oh, the speed of sound. Well, there are two speeds. So there is a longitudinal and transverse phonons in the system, and at that frequencies, these longitudinal phonons have velocities of around 8 kilometers per second and 4 kilometers per second for transverse.
Okay, thank you.
All right, thank you. I'm not seeing any further questions in the list of participants or in the chat, but I was going to ask myself one thing, which is that what happens to this thermal formation process, which you've described, if we assume the system is at a very low temperature to start with?
Oh. Well, if the temperature, so basically you're asking if we will do the perform the experiments at
Cryogenic temperature.
at the energy, basically at the thermal energies of about magnons, so
yeah.
millikelvins.
Yeah.
So well, to start with, there are no experiments done below 10K. On this system, on the pumped Magnon spectrum so far. So I'm really looking forward to do this, do such investigations experimentally. So yeah, and it's I'm open for collaborations. From the fundamental point of view, if we consider the experiment with pumping, parametric pumping experiment for creation. Well, first of all, the pumping process will be pretty much the same, I suppose. We need to be concerned about heating of the system, obviously, but in terms of that, it should be a much lower threshold, because first of all, the damping, well, and even more importantly, I would say that it's just because the threshold of the process basically depends on the chemical potential, how much chemical potential will rise at low temperatures. It would be much easier to achieve the threshold. And we could essentially observe the condensate out of thousands of magnons probably at low temperature. So this is the idea. Though the question is how to measure it with like optical technique. It's quite a very good question because of the necessary high rate photons rate. So which will heat up the sample inevitably. So this is the problem. And the microwave detection is associated with the making very nice small microstructures. So which is not a problem for superconducting technique and for modern lithography, but it's always been a problem in if you work with macroscopic samples and do the experiments. So far, all this field has been plagued with from basically lack of transition between macro and micro structures. So this is it. In terms of the interest towards the single magnons experiments, yes, this is indeed will bring a lot of interesting and non-classical physics into the magnonics, because we could do all sorts of single magnon experiments. So using the parametric down conversion, I believe that would be very interesting to finally investigate it in a single magnon regime.
Okay, one final question by Krisha, maybe it's a comment, I don't know.
What happens if magnetic field is normal to the film? So why you don't do the experiments, and what is your opinion about Bozhko experiment?
So the difficulty there is the following. First of all, the condensate in perpendicularly magnetized film will form at wave vector equals 0. So around that wave vector, it's not, first of all, it's not possible to talk about pure magnons itself, because those magnons are hybridized with electromagnetic waves at very long wavelengths, right? So this is first thing. It's not a pure magnon in there, but though it has no obstacles to observe the condensate there. The main problem in this system is that in particular magnetized films, there is a nonlinear frequency shift, which actually does not decrease the frequency, but increase it, because when you excite more and more magnons in the out-of-plane magnetized film, due to the Dirac factor, you decrease the magnetization of the sample, and thus the internal field increases, and that brings the frequency of those magnons and those polaritons up. And if you excite a wave at higher frequency, where you pump, for instance, you pump it with ferromagnetic kind of just above the ferromagnetic resonance. You excite some not not the vector zero magnons, but you excite a lot of them. And then your point of the bottom of the spectrum just shifts up to the point where your excitation is. And at that point, you already start to just drive resonantly your system. And system self-stabilizes at that particular point. This self-stabilization of the system, in my opinion, it's not, it's quite hard to tell that it is a condensate when you just forcefully excite the system at particular frequency. This is ferromagnetic resonance. This is nonlinear frequency capturing of locking. It's quite hard to tell that it's condensate. So that's the if one would excite magnons at sufficiently high vectors and completely exclude the influence of the excitation on the condensate itself, so no direct energy transition from the pumping source to the condensate, then yes, then that would be the good proof. But so far I haven't seen that in the experiments.
Okay, thanks.
Right, thank you very much. I don't think there are any further questions, and also we've used plenty of time already, so I think it's about time to conclude this. Let me thank the speaker for a very interesting presentation today, and also the audience for active participation in the discussion.